Okay, I wanted to give you an example problem for classical lamination theory. Very, very similar to the homework, but not exactly the homework. But I think this is an important step to help you guys kind of go through the equations and see how the equations are actually applied. Because I know it can get a little abstract. I don't want you to use this as a complete crutch to not deeply understanding the equations, but I do think that this is very, very helpful. Sometimes I know, like myself, I needed to see it to kind of understand the math equations in the beginning. So hopefully this will help you clarify a few points in the entire process and in all the equations. Okay, so let's do a 0.90 symmetric where every ply is 0.1 inches thick. So you can see here I got a 0.90, 0.90 laminate. At my midplane here, Z is going down. We'll talk about the Z coordinates. I think there are a lot of questions from students on how the Z coordinates work. I think when I get to that, that should clarify that. I'm just going to use some generic completely made up properties, but E1, 10 e to the 6, E2, 1 e to the 6, about an order of magnitude less, which is about what it is in unidirectional carbon polymer matrix composites. Poisson's ratio 0.3, G12, 1 e to the 6, alpha 1, 1 e to the minus 6, and alpha 2, 10 e to the minus 6, which is about what it is, about an order of magnitude greater in the two for alphas versus the reverse in stiffnesses. We'll calculate all of our equations and then apply a minus 100 degree Fahrenheit delta T and a NX of 1,000 pounds per inch to get all results. Okay, so that's the problem that we're going to set up. I'm just going to walk through the solution to this through the recipe that I gave you, and I'm going to do it in Excel. Not that I ultimately recommend Excel. I just really like Excel for teaching and education purposes, mostly because you can see all the numbers at intermediate steps. And so while, ultimately I write these things in Python or C++, that's what I write them in. You could write them in anything ultimately, MATLAB, Mathematica, Python, C, Fortran, whatever, you're the most comfortable with. But I really like doing it in Excel, at least the first time through, just because, like I said, it's easy to see the intermediate step, every single value intermediately. Of course, you can do that with all the other ones with debuggers and all the other things that are available these days. But this is just the way I set this up in Excel. I kind of learned the most efficient way to do this over many, many years. So I'll show you that the way I would. Not that you have to set it up this way, but I think this is probably the easiest. Okay, so let's start with our step A, kind of getting our information. That's why it's step A, not step one yet. And for every ply, you can see the way I've laid this out is a little table, right? I give a ply number here, so we have 4 plies, 1 through 4. You'll have 8. The thickness of every ply, the orientation of every ply in degrees. You'll see later in Excel I need radians, so I'll calculate radians later. But it's Young's modulus in the one direction, 2, Poisson's ratio 1, 2. Now, remember in some of our equations later, we'll need V21, so I'll fill this in a little bit later. I'll just put a space there for it for now. And then our shear modulus in the 1-2 plane, our coefficient of thermal expansion in the fiber direction, and our coefficient of thermal expansion in the matrix dimension. And I got that for every single ply, all the data filled out for all plies. Okay, so step A is basically done. Let's move on to step 1, where I have to calculate the plane stress stiffness matrix in the 1, 2, 3 material system. So this is our Q1, and I have to do that for every single ply. Well, easy enough. I have the data for each ply. I simply set some headers here so I know that I need to calculate. Remember, this is Q11, Q12. Remember, Q14 is 0, right? And then Q22, Q24 is 0, and then Q44. I don't need to calculate the bottom triangular half of this matrix because it's symmetric. So I only need the 4 components to calculate to fill out the entire matrix. Okay, so let's calculate Q11. It's E1 divided by 1 minus V12 times V21. So right away here is where I need to calculate this V21. So what is V21? Well, if you remember the equation, Vij over EI equals, let's see, I'm going to need to erase that. So Vij over EI equals Vji over EJ. So, doing that out, V12 over E1 equals V21 over E2. V21 equals E2 over E1 times V12. Okay, easy enough. So I can fill that in. So equals E2 divided by E1 times V12. And I simply copy that down. Okay, now I can go back to calculating my Q11 component, which is right here. Okay, so now that equals E1 divided by 1 minus V12 times V21. Close out my parentheses, and we're good. Okay, then I can calculate 1, 2, which is equal to V12 times E2, close that out, divided by 1 minus V12 times V21. I can calculate my Q22, which is here. So that's going to be equals just E2 divided by 1 minus V12 times V21. And I can calculate my Q44, which is right here, which is just G12. Okay, so that's all done. Now I need to do that for every ply, right? But I'm gonna just do one ply first. You'll see the way I do this. Do one ply completely, and then if I set up the equations right, I can literally just copy it down for every ply. Okay, so we're gonna hold on the every ply for now. We'll finish one ply completely, and then we'll copy everything down. Okay, so what's the next step? Well, the next step is I have to transform the plane stress stiffness matrix in the 1, 2, 3 system into the global XYZ system to get my Q bars or my QXs, right? And so that's these equations. They're long. It just takes you, 20 minutes. But the good way about the way I set this up is you only have to do these for one ply, and then when you copy down, you never have to do them again. So I'm just going to do one of them. I've actually got all the other ones filled out here. So we're going to do Q bar 1, 1. So Q bar 1, 1, we're going to be doing this equation right here. The 1, 2, 1, 4, you can see the 1, 2, 1, 4, the 2, 2, 2, 4, 2, 2, 2, 4, and the 4, 4 I've already done. So, if you click on them, you can see they're already done. But one of the things we're going to need in order to do this is theta in radians. So here's where I got to fill out the radians of my angle theta, which is back here. And then I can just Control C, Control V that down. And I've got my my angle in radians that allows me to do my Excel properly. Okay, so let's just move this over a little bit to what we're going to need. There we go. And so now I'm going to run the Q11 calculation. And this equals, see if I can do this right, Q11 times the cosine of theta raised to the 4 plus 2 times Q12 plus 2 times Q44 times the sine of theta raised to the 2 times the cosine of theta raised to the 2 plus Q22 times the sine of theta raised to the 4. Okay. And I've got that equation put in. I can, double check it, whatever I need. And then I've obviously already written the other one. So Q12, which is here, I've got that all to find out. And this part is just, like I said, it's a 15, 20 minute exercise, but you only have to do it once because if we do it, set it up right, then everything else is just a copy down. Okay. So that is done. And now the part that I think some students are confused on and took me a while to get it too. So is this calculating the ZK coordinate, or I should say the Z coordinate for every kth ply. And you literally, I draw this image out for the laminates that I have quite often. So let me do that, when I was first learning this. So let's just do that for our 09090. And the first thing that I do is I always calculate the total thickness, right? And so that's easy enough in our spreadsheet, actually. If I know the thickness of every ply here, all I have to do to get the total thickness is I could just sum them up. And of course, this is going to be 0.4. So now the middle surface is always our datum plane. And I might not have made that clear in lecture, that the middle surface is always our XYZ. And that's really our Z of 0, right? And so everything goes off of this middle plane. Well, our middle plane, I have 4 plies, is in between ply 2 and 3. And then once I have that, then I know that I always stack in the direction of the normal, so that this is ply 1. I should probably even put that in here, right? This is ply 1, this is ply 2, this is ply 3, this is ply 4. And so then I can say, okay, then Z naught is the distance from my middle surface to the bottom. I know this sounds weird. It's the bottom because, remember, my Z is going down, so it's kind of opposite of the way you draw it. But you'll see why the convention is this way. Ultimately, it's to make sure that our moment signs are consistent with that of strength of materials that you're used to. So you'll see almost every textbook draws Z going down, positive going down. So Z naught is the distance from the middle surface to the bottom of my laminate. Well, that's just T minus T over 2, right? And so, because if I'm at the middle surface and T is 4, then the distance to Z naught is minus O2. And then all I have to do to get to my Z1, which is the distance to the next interface. So remember, the Z of every ply is always the top of every single ply. It's the largest, right? Because Z naught is going to be the bottom, and then everything else is the top of that ply. And so all I have to do from Z naught is if I add the thickness of that first ply, so the thickness is 0.1, I get minus 0.1 to get to this dimension. And if I add a thickness again, I get to 0. That gives me my Z2. And then if I add a thickness again to get to Z3, I get 0.1. And then if I add a thickness again to get to Z4, I get 0.2. So that's all you have to do after that is you just keep adding the thicknesses of every ply. If they're not the same thickness, it's still, the algorithm still works. But it always starts out with a Z naught. So I always start out, this is why I have one blank row here, very key, because I have to put a Z naught in here, right? And this is always equal in the case of our class. This is not true in general, but in our class, this will always be equal to minus the total thickness divided by 2, because I'm finding that bottom surface from the midplane. This is where we get into offsets, and offsets I cover in 551, so that's kind of the next class. But in our class, just a little bit of forewarning. In our class, we will always just do no offsets, that the laminate middle surface will be the middle surface of the laminate. And so Z naught is always minus T over 2 in our class. Okay, well then what do I have to do to get to Z1? Well, I just have to say, okay, it's the prior Z plus the thickness of that particular ply. And then once I've set up this equation, it's always the prior plus the thickness, prior plus the thickness. So I can just copy it down, and you can see that it copies down right, and I always get the right ZK for every single ply. And so easy enough to get. So hopefully that helps you understand. ZK is a scalar, right? It's a coordinate dimension, so it is a scalar at the end of the day. Just someone had asked that. Okay, well, let's go. So now I've calculated ZK for my laminate, and I'm ready to move on. Okay, now what I need to do is I have to transform. So I was given the coefficients of thermal expansion in the material system, and I need to transform those into global, because remember, we're getting everything into global, and we're going to sum everything up. And so I have to transform those into global. And so all we're going to do is I'm just going to perform these calculations. It's written here in matrix math. Here's my AX, AY, AZ. I'll just do one of these out for you, right? So alpha x is equal to the cosine squared times alpha 1 plus the sine squared times alpha 2 minus the cosine sine times alpha 1, 2, right? So all I did was this row here times that column, that first one here. Okay, and then you could do the second one for alpha y and the third one for alpha xy. And I think you can see that as I go through this, how that'll work. So this is equal to the, I'm just going to do it in reverse order here. So alpha 1 times the cosine of the radian squared, and then plus alpha 2 times the sine of the angle squared. And then remember, in our material system, alpha 1, 2 is always 0 because you don't get a shearing strain due to a change in temperature for a ply in the material system, which means all this goes away, which means I don't have to calculate any of that at the end of the day in this particular case. And so I'm done with this equation over here. And I get my alpha x, which should be the same as what I had because it's a 0 degree ply. And then I can calculate my alpha y, so that's equal to alpha 1 times the sine of that raised to the 2 plus alpha 2 times the cosine of that raised to the 2. Okay, and then my alpha xy is going to be equal to 2 times my alpha 1 times the cosine of theta times the sine of theta, and then minus 2 times alpha 1, 2 times the cosine of theta times the sine of theta. Just finishing off that third, calculation right here in this math. Okay, so now I've got my alpha x, alpha y, alpha xy. Everything looks good, and I'm ready to move on. Okay, so now what I have to do is we have to calculate the A, B, D, and the NXT and MXT. We're going to start with the ABD matrices. And what you can see here is eventually I'm going to sum K equals 1 to N. So this equation here, if you would, if I were to write that out just to make sure, is, Q bar 1 for the first ply. So don't get confused. I guess I should say Q bar X comma 1 for the first ply. Actually, this is why we use bar and not, so don't get confused with my terminology. I'm going to write Q bar, which tells us what coordinate system it's in, and then the 1 here is the ply that this is coming from, not the coordinate system that it came from. So maybe a little bit of information as to why we use the bar. I don't think I had gone through that before versus kind of putting it down here where I told you our convention. So I just kind of changed the convention on you a little bit. Times a scalar. So it's going to be Z naught minus Z1, right? It's the K minus Z1 minus Z naught. And then plus, Q bar 2 times Z2 minus Z1. And then plus, Q bar 3 Z3 minus Z2, right? And then this goes on and on and on to the nth ply. And when I talk about the kth ply, any intermediate ply is the kth ply in the sum K equals 1 to N, right? So hopefully, me writing this out just makes it a little clearer, what this equation actually is. It's just a sum, written all the way out, summing it to N of these, and any intermediate one is the kth particular, whichever one I happen to be on. Okay, so what we're going to do is we're just going to do the first one for all of these, right? And then we'll copy and sum the rest of them down. Okay, so just to be clear, this is a 3x3 matrix, and this is a scalar. So I'm just multiplying a 3x3 matrix times a scalar. That means all I have to do is I can take every component of the 3x3 and just multiply it by the scalar number. So Q11 times the scalar, Q12 times the scalar, Q14 times the scalar, Q22 times the scalar. So, multiplying a matrix by scalar is really easy. It's just every component multiplied by its scalar. Okay, so A11 is just going to be equal to the Q bar 11, right? Make sure it's the bar because we're all in global now, times the scalar, which is ZK, which is here, minus the ZK above it, which is there. Okay? And then that's it. That is my A11. So what is my A12? Well, that's equal to Q bar 12 times the scalar again, right? Times my ZK minus 1. Okay? Now, if I do this right, you notice I've got this set up where, Q bar 11, 12, 14, 22, 24, 44. These are all the terms I need in my A matrix. And I've copied that the same here, 1, 1, 1, 2, 1, 4, 2, 2, 2, 4, 4, 4. The only thing that I don't want to have copy over are the ZK minus ZK minus 1. So all I have to do is $ out the columns in my first equation, and then I can just copy this directly over. And you can see here that then that's Q12 times the difference in the Z's. The 1,4 is the 1,4 times the difference in the Z's. And the 2,2 is the 2,2 times the difference in the Z's. So it's very, very easy. Just do one of them and then copy them all over. Okay, well, let's do the B. Let me do the B here. The B is, so this is the A. The B is the same Q bar, right? But now it's Z1 squared minus Z naught squared, right? And then plus Q bar 2 times Z2 squared minus Z1 squared, and then plus, and then you guys can keep going from there. Okay, so all I need to do for my B's is kind of the same thing. So B11 is equal to my Q bar 11 times a scalar, and that scalar happens to be the ZK coordinate raised to the 2 minus the ZK coordinate above it raised to the 2. And then that's it. And then again, if I just don't want to allow that to move when I copy it over, I put my $ in my columns. And then when I copy over, when I go to the B12, I always check. It should be my Q bar 12, which it is, and then my same ZK minus 1. Okay, so I've got my B's done. Okay. Now, how do I do my D's? Well, it's the same thing, only it's going to be cubed instead of squared, okay? And you're going to say, hey, Jeff, what about the 1/2? You notice the 1/2 is after I sum it, and I haven't summed everything yet. Remember, so far, all I'm actually doing is calculating this very first one here, and we haven't performed any more of the sum. So let's go ahead, and then when I do sum it, then I'll add the 1/2 and 1/3, you'll see later. So what is D11? Well, that's just equal to, Q bar 11 times the ZK cubed minus the ZK above it cubed. Okay, and then if I $ out my columns as I copy across, everything will go properly. And I always check, make sure that it copied right. So my D12 should be my Q bar 12, which it is, and my ZK minus 1 cubed. Okay, so I've got all my A's, my B's, and my D's done for one ply, right? So now what do I have to do? Well, now what I have to do is I have to perform the sum. So I have to now do it for every single ply. I haven't done my NXT and my MXT, but I think I'm going to do that next. I think I'm just going to go through these equations and sum them right now. I think it's just easier for you to learn that way. Okay, so I've got one whole ply done. So if I take this entire ply all the way through here, and I copy it, and I paste it into the rows below, I've now got these calculations done for all 4 plies, okay? And then I have to sum the A's, the B's, and the D's. And so all I have to do is come over to my A, B, D's now. So here's my A, B's, and D's. And I have to say, well, the A's, it equals the sum. The total A11 will be the sum of of that whole thing. And then I can just copy that across. So I just calculate a sum. So this is my A matrix. And then for my B matrix here, remember, it's the sum divided by 2. So it's just equals the sum of each component. And then I can't forget to divide by 2. Okay? And then I can go ahead and copy that over for all my B's. And then my D's, again, remember, it's the sum divided by 3. So this equals the sum divided by 3. And I can go ahead and copy that all the way across. So at the end of the day, pretty easy. Now, what I'm going to do to finish this off is I want it to be in this matrix form, and I kind of have it in this row form. So it's really easy to get it in this matrix form. This is the A11 component, so I just say equals, and then I go over to my A11 component here, and I pick it. That's the one I want. And then all I do, and I can just say here, this A12 is equal to this A12, so I pick that. And then the A14, which is here, is going to be equal to A14. And then, my A22, which is here, I pick my A22. There's a faster way to do this, but I'm actually just doing it more explicitly so you see it. This is going to be the A24 component. So there's my 24. And then here's my A44 component. Okay, and then if I do the same thing for the B's, equals the B11. Now, the way that I have this set up, the 1, 4 or 1, 1, that's the 1, 2, and 1, 4 are the next in line, so that's perfectly fine. I just copy across. I'm just showing you the faster way to do it. And then my 2, 2 component, and I can copy the next one because that's my 2, 4, and then I can just say my B4, 4 component. Okay, so now I got that B matrix filled out. Now you notice I haven't done the symmetric part of it yet, right? Which I'm going to do last. So here's my D. So this is equal to D11. So if I come over here, again, just to be clear in what I was doing, remember there's the D11, D12, D14. So if I just copy the next 3 over, I'll get the first row, right? So Control C, Control V, Control V, and then this is the D22. Which, there it is right there. And the next one over is D24, so I can just copy that over to 24. And then a D44 to finish it up. Okay, and now I can finish, all stiffness matrices are symmetric, so I can just fill in the symmetric parts of this. And there we go. And then obviously to make this whole thing symmetric, this just has to be the transpose of the top, and that makes the whole thing symmetric. Okay, so I've got my complete ABD matrix calculated. We just ran these 3 equations. Now let me do the, let me go ahead and do the, and I think this will be good. I'll go ahead and get rid of this because I think it's clear now what that is all about. Now let's run the NXT, MXT calculations, okay? So one thing I want to make clear on this is that, again, it's the summation. So it's this whole thing repeated, so it would be Q bar 1 times alpha, now X1. I had to say in the X system where the bar here tells me it's in the X. I guess I could have said X comma 1, where the second subscript is the ply, times Z1 minus Z naught, and then plus, Q bar X2 times alpha X2 times Z2 minus Z1, right? And then plus dot, keeps going all the way to the nth ply. Now, remember, this is a 3 by 3. This is a 3 by 1. So I end up here with a 3 by 1 when I do that. And if this is a scalar, And when I multiply a 3 by 1 times a scalar, I'm just multiplying the 3 by 1. So what I get at the end of the day here is a 3, in this calculation is a 3 by 1, whereas before I ended up with a 3 by 3, right? So what's only going to change here is that we added this extra matrix multiplication. And so I've got to do that. So just to remember, so if I have, Q bar 1 1, Q bar 1 2, Q bar 1 4, Q bar 1 2, Q bar 2 2, Q bar 2 4, Q bar 1 4, Q bar 2 4, got a little Q bar 4 4, right? That's that whole matrix. And I'm multiplying that by alpha x, alpha y, alpha xy, which could be a number now. Now, if I do this whole math out, I'll just do one of them to get my first term, if you would, the kind of, I'll just call it nxt prime, right? It's this nxt prime nyt prime, because it's not the full equation yet. That's why I'm just giving it a prime. I'm just doing this row times that column for one of them, right? Just so you see what I'm doing here. So it's going to be Q bar 1 1 times alpha x plus Q bar 1 2 times alpha y plus Q bar 1 4 times alpha xy. And so I have to do that for all of them. I got to do the next row, right? And then I got to do the next row for each one of these. I just got to do that fully out before. Then I have to multiply this by the scalar, which would be the z k minus zk minus 1, right? Gets added on the back of that after I do this whole thing out. So I want hopefully that helped you a little bit. I know it's a little tight and a little messy, but that is this whole thing kind of written out. Obviously, I haven't done the sum yet, so I haven't worried about the delta t yet, because I'm just worried about this part of the calculation so far. Okay, so hopefully that is helping you make sense of these calculations. So here's my nx of t. I need to go ahead and run this. So this is going to be equal to my Q bar 1 1. There's my Q bar 1 1 times my alpha x, not my alpha 1. You got to always remember what system you're in. Remember I told you, understanding the systems you're in is incredibly imperative. I'm working in the global now, and so I need my alphas in the global. I already transformed them, so those are the ones I want to work with. I'm working with plane stress stiffness matrix terms in the global, and I'm working with coefficients of thermal expansion in the global. So just that's another place where students kind of go awry. Always make sure that you're kind of working with apples to apples and that you're not mixing apples and oranges. That's a big thing. Okay, and then, Q bar 1 2 times the alpha y, and then plus, I guess I can leave it that, Q bar 1 4 times the alpha xy. And that's the first part of that. And then I need to do my zk minus 1 on top of that, but I forgot a little times sign there to multiply. And that is my first ply nx. But then I have to do the second, still first ply, but second term. So equals, now I'm working on this one. So it's Q bar 1 2, Q bar 2, Q bar 1 2 times alpha x, Q bar 2 2 times alpha y, Q bar 2 4 times alpha xy. So let me go back over here, expose everything. Here we go. So now it's going to be a 1 2 times alpha x plus a 2 2 times alpha y plus a 2 4 times an alpha xy. So it's just matrix math in long form. Obviously, this part would be much, much nicer in something like MATLAB, right? Or Python with like a SciPy or NumPy, probably NumPy add-on. Okay, then I need my zk minus 1. So zk minus zk minus 1. But again, I like doing it in Excel this way because it's really instructive. You're really deeply understanding what's going on with these equations. It's kind of have to see it all. Okay. And then I can do my third term, which is going to be Q14 times alpha x, Q24 times alpha y, Q44 times alpha xy. So let me expose everything here. And I think I can even expose to there. Okay, so equals, now I got to go alpha 1, 4 times alpha x plus 2, 4 times alpha y plus 4, 4 times, and I didn't get the alpha y in there right, times alpha y, there we go, plus the 4, 4 times alpha xy. And hopefully at the end of all this, I'll check to make sure that I haven't made a typing mistake. I do make typing mistakes, but we'll check just to make sure. Okay, now I got my nxy. Perfect. Let's go ahead now, and I have to do the same thing for the moment. But I'm not going to redo this whole thing. The only thing that changes in the moment, every part of the derivation that I just went through is exactly the same. The only thing that changes is I'm going to square the scalar term instead of leave it as a power of 1. So literally the easiest thing to do is nothing changes in my original equations. Is I literally just copy the equations over, and then I just square the zk terms. And my last one here. Okay, so now I have these calculations done for one ply. Well, now I need to do the sum. So how do I do the sum? I simply copy it down. My last ply here is my sum. Then maybe I'll make that very clear that this last ply is actually a sum by giving that a slightly different color here that I call it the calculation color, just to make that very, very clear that that's my sum. Okay, now the nxt is just the sum times delta t, but I'm not going to worry about the delta t right now. I'm just going to sum them. I'm going to apply the delta t later. So I'm just going to go the sum of those components, and I'm going to copy it over to the other ones. Very good. All looks good. And then the same thing for mxt. It's the sum, but I'm going to use the half. I'm not going to leave the delta t out. I'm going to put the half in right now. So this is going to be the sum of all of this divided by 2. Okay. Perfect. Order is restored, so it should be 0. Okay, so now I've got my nxt's and my mxt's without a delta t applied. So I still have to apply that delta t. And what you're going to see here is I really need to get it into matrix form. I have it in kind of row form. So all I'm going to do is kind of copy it into here. So here's my nxt. I'm going to pick it, nxt there. And then what I will do is, and then this is nyt. There's nyt, and then equals nxyt, my equivalent shearing force, and then my moments. So that's mxt, equivalent moment thermal, which is there, and then my myt, just reordering this from row to column form to put it in my matrix form that I need it in. There we go. So now I have the equation starting to get filled out. Remember, the equation is I kind of wrote the reverse of it down here, but the reverse of that is let me see if I can get my oops, because that what we had before was n m equals my a b b d times my mid-plane strains and my curvatures. Put that in not there. And then minus my NM's, equivalent thermal. And then, we're going to invert that. But you can see that my top row here is just nothing more than that equation. But I need to multiply these by the whatever delta t it is that I want to apply. So you might want to change that, which is why I leave it out so you can change it quickly later. So I'm just going to put the minus 100 for our thing, and then it's just equals every term times that minus 100. And when I copy it down, I don't want the minus 100 to change. Oops. So I'm going to $ out both the column and the row to make sure that doesn't change. And that's my equivalent thermal forces and moments for a minus 100 degree change. So this would be like you cured it. We always cure at elevated temperature, and then we bring it down. Okay, we don't normally run the equation, excuse me, this way, but I'll go ahead and perform this calculation anyway. Let's say I apply 1,000 microstrain in the x direction with all other strains being 0. Remember, this would be like my superpower on the other faces where we're not allowing the other faces to move, which is typically why we don't apply the equation this way. But we can do it anyway. So the resulting force would be equal to the multiplication, mmult, of the ABD times the midplane strains and curvatures minus the equivalent thermal forces and moments. And then I get those results there. But normally we're going to be running the equation this way, as shown in equation 6. So we have to invert the whole equation around. It means I have to calculate the inverse of the ABD. So that's easy enough. It's just M inverse of the big ABD, and I get that. And then normally we would be applying, or in our problem here, let me just make sure that I got it right. What did I say? 1,000 pounds per inch and a minus 100 delta F. So we already got the minus 100 delta F. We would normally be applying some load, 1,000 pounds per inch, and then my total load is going to be equal to the applied plus the thermal. As you see in the calculation here. And then I can just go ahead and do my matrix math, which is equal to the mmult of my inverse ABDs times my total forces. And I go ahead and get my strains, my midplane strains and curvatures, midplane curvatures back out from that particular calculation. Okay, so now we've got step 6 done. And effectively at the end of step 6, we've transformed everything into global, summed everything up, and then solved our problem. And now we're going to unravel everything back to local. So we're going to kind of do the reverse process all the way back to local for every ply. Okay, let's go ahead and do that. What I do to start this process is I just copy the information back down to a row. So I copy all the information associated with the stacking sequence itself. And then I copy also the plane stress stiffness matrix in the material 1, 2, 3 coordinate system. Okay, the next thing we got to talk about is this, where we want to get the results out at. And I think that's my slide 36, which I did not review in lecture. But we can talk about quickly here. You can, in the equations, you need a z coordinate for that ply. It doesn't have to be the zk we talk about. It doesn't have to be the top, z naught or z1. It can actually be any z in the kth ply. So if you look at it, there's an infinite number of z's in every ply, right? So any z coordinate between z naught and z1 would be an acceptable z to get a result in for the first ply. Another example would be any z between z2 and z1 would be an acceptable z to get a result in for the second ply, and so on and so on. By default, most codes will give you the midplane of every ply. I actually prefer to get the top and bottom of every ply, because if you think about it for a second, the top and bottom always have to be would have to be a max or a min, would have to be. And so if you get top and bottom, you kind of cover everything, but kind of historically by default, Most codes will just give you the midplane. So we'll just work, and since we don't want to get too complicated here, I'll just do the midplane for every calculation, which means I just need to calculate a new z. Well, that's easy enough. For every ply, it's just going to be the sum of the top plus the bottom divided by 2. And I can just go ahead and, copy that all the way down. So I have the zth coordinate of the middle of that ply that I want to calculate information at. Okay, good. Now let's go ahead and run our equation. So I know that I want to get the total strain. Remember, we got to always remember that there's total, mechanical, and thermal strain. And we always start with total because we have totals yet. So the total strain in the global system for this ply, well, that's nothing more than the midplane strain plus z times the curvature. Well, here's my midplane strains right here, and then here's my midplane curvatures. And so all the total strain is in the global for every ply is just the midplane strain. So if it's EX, right, if I'm just summing these up, maybe I should do this out here, right? So if I got EX, EY, gamma XY, in the X coordinate system for the kth ply is equal to EX naught, EY naught, gamma XY naught, plus Z of some Z in the kth ply times kappa X, kappa Y, kappa XY. And you can put the knots on here if you want, just to say that these are midplane strains. And I'm now getting it in every ply, and that where I get it through every ply is through this ZK. So you just sum this up. The first one is EX naught plus Z times kappa naught. The second one is EY naught plus Z times kappa Y, et cetera, et cetera, et cetera. So it's just that plus, plus the zth coordinate of that ply times the curvature in that direction. And that's it. And then if I want EY, it's just the midplane strain in the Y direction plus the Z coordinate of that ply times the curvature in that direction. And if I want the shear strain, it's just equal to the shear strain plus Z times the curvature. Okay. Good enough. Now, if I wanted to copy that down, realize I don't want the midplane strains to go anywhere when I copy it down. So we're going to $ off the row for every equation here so that it doesn't get copied down. Okay, now if I copy that down, I have the, and I always check, like say the next one, just to make sure that, picked up my ZK of that ply, and then it did not change my my midplane strains, which is correct. I'll just check another one, and that's all good. So we're happy with that. Okay, now I have the total strain in global. That really isn't super useful. I really want the total strain in material. So I have to transform everything into the 1, 2, 3 system. Okay, well, I have it in global. I have my angle. And so all I have to do is transform. So just to be clear here, all I'm doing again is I'm running this equation, right? This row times that column gives me that result. And then, then this row times that column gives me the second result, and so on and so on and so on. So let's just run these equations. So it equals, this first one is going to be EX times the cosine of theta raised to the 2 plus EY times the sine of theta raised to the 2, yes, plus gamma XY times the cosine of theta times the sine of theta. Okay. And somewhere I have put in one too many. There it is right there. There it is right there. Perfect. And perfect. And then I can run E2. Again, this is the second, so it's going to be equals to EX times the sine of theta raised to the 2 plus EY times the cosine of theta raised to the 2, and then minus gamma xy times the cosine of theta times the sine of theta. Okay, that's good. And then gxy equals minus 2 times EX times the cosine of theta times the sine of theta plus 2 times EY times the cosine of theta times the sine of theta. And then plus the gamma xy times the cosine of theta squared minus the sine of theta squared. Close that off and I should be good. Perfect. And then here I should be able just to copy everything down because there's everything was set up once, so everything works, and that looks correct. What you see here is for my 90-degree plies, these numbers should flip, right? So at 90-degree transformation, EX becomes EY, EY becomes EX, and that's exactly what happened here. So again, just checking your numbers as you go through with what you'd expect. Okay, so I've got now everything in the 1, 2, 3 system. Well, now, if ultimately I want to calculate stresses in the 1, 2, 3, I have to get to mechanical, right? So what is mechanical? Well, mechanical is the total minus alpha delta T. Okay, I have my alphas in. Now you have to remember, now I'm in the 1, 2, 3 system. So now I have to use alpha 1, 2, 3s, right? So again, the whole apples and apples, not apples and oranges thing, right? So I'm in the 1, 2, 3 system. I have to stay in the 1, 2, 3. Now it's the mechanical strain is the total strain minus, here's my alpha in the 1, 2, 3, alpha times delta T. My delta T is back up here. And then, E2 is equal to the total strain in the 2 direction minus alpha 2 times delta T. And then my G12 is equal to the total strain minus alpha delta T, but there is no alpha 1, 2 because it's a orthotropic material, right? There's no extension shear coupling in the 1, 2, 3 system. So don't get confused. Another place where a lot of students get confused. Alpha 1, 2 is 0. That's why we just don't put it in. So there's, the minus 0 times delta T is still a 0. So it is just the total strain in that direction. Okay, now the only thing I need to do is $sign out my delta T to make sure that it stays when I copy things down. Otherwise, everything else can remain. And I'll just check one of these E2 so I know it should be my alpha 2 and my E2 and my delta T. And so I'm happy. These are my mechanical strains now in the 1, 2, 3 system. And you notice they're going to be different than my totals because I have an alpha delta T. And now that I have my mechanical strain, now I can finally calculate my my stress. And just to remember again, this calculation, I've got stress 1, stress 2, tau 1, 2. I'm just expanding this out. Equals, Q11, Q12, 0, because I'm in the material system again. Q12, Q22, 0. 0, 0, Q4, 4. Remember, there's no bars because I'm in the material system. Times the strain 1 mechanical, strain 2 mechanical, gamma 1, 2 mechanical, right? And so I'm just going to, do this out, right? This row times this column to give me that number, and then the same thing for the other ones, right? So now it's easy enough to get my stresses. Let me show everything I'm going to need. There we go. So, equals E1 mechanical times Q11 plus E2 mechanical times Q12. There's a 0 in the next one, so I don't need to do anything, and there's my stresses. And then this is going to be equal to what do I got here? Yeah, Q E1 times Q1 2, and then plus E2 times Q2 2. And then this one equals just gamma 1 2 times Q4 4 in my calculation. Okay, and I should be able to just copy this all the way down. Okay, very, very good. And then that's it. My complete analysis is done. I have my strains and my mechanical strains in the material system and the stresses, and these are ultimately the numbers that we're going to work with. A lot of times I'll just make this a little bit more obvious. I'll block these out so that you can kind of see that. Okay, let me do one last thing here. Well, I'll do this off the video, but I'm going to go make sure that this is all correct, just to make sure I haven't made a mistake somewhere in my calculations. And then I will, post this video for you guys, and I'll probably even, give you this spreadsheet just so you have it. I hope that this helps, and I will send an email out, with all this. I will also, because this is very important, and I want you to really take your time to get this right. I'm going to give you until Friday at midnight to complete the homework this week. So a couple more days, you got the whole week. But I want you to use the extra time to really go through and now that you've seen kind of an application, hopefully that helps you when you go back through the derivation, that the equations make more sense. Go back through, derivate everything again, like I did in the lecture, the lecture on Wednesday night. Now that you've seen it applied, take a look at this, reapply it again. If you set it up, right, the two homework problems should be as simple as just typing in a few numbers and hitting the button. You'll get the answers. And that's the easy part. The part that I really want to make sure gets solidified is a deep understanding of the equations. I really don't want to just plug and chug the equations. I really want a deep understanding of what we're doing, why we're doing it, what system we're in, what system I need to get to, how I do that, how I go forward through the equations to get to global, how I go backward to get back to local. These are the concepts that are the absolute foundation of composites. I know that you guys are asking a lot of questions about, how to apply this stuff in your jobs every day and this and that and everything. And I hope I can convince you that in order to answer all those questions, you have to have a solid foundation in all of this. And that once you have that solid foundation, all the answers to all those other questions will become much, much easier, and it'll make a lot more sense. So I think really taking your time with this, really understanding, you guys are asking great questions. Continue to ask those questions because this is that important, I believe. Okay, thanks.